Thank you. Thank you all for joining me today. As mentioned, I think it was well started here with my introduction, but my name is Priscilla Parodi. This is my email address, so if you have any question, feel free to send me an email. This is not a problem at all. This is my LinkedIn profile, so basically the name and first name and last name. So feel free to add me there, to connect, to send questions, and to talk about anything tech related to besides Elastic, of course, and the content of this presentation. As mentioned, of course, we'll have time upstairs, so feel free to ask me questions there. If you have time, I can also answer some questions here. But besides that, use the social media too, because I'll be there all the time. So let's make it work. Okay, so today, as mentioned, we are going to talk about improving retrieval quality for search. And this is the agenda. So we'll start by revisiting text search, known as lexical search. Then we'll talk about vector search. I'll introduce it to you. Then semantic search with dense vectors, then with sparse vectors, more specifically, learn it, sparse retrieval. And then finally, we'll talk about hybrid retrieval. But first, and before we get started, what is Elastic? Do any of you know what Elastic is, what Elasticsearch is? Cool, good percentage here. So let me explain here for the others. Elastic is a search company. And usually when I tell people that Elastic is a search company, they come up with this search box because of Google and all of the examples that we have. And actually, this is a great front end and a great example here. But in fact, search goes beyond that. Think of Uber, for example, which is a user of Elastic. So, of course, you have the search box at first where you type the address. But besides this, if you think about the core of Uber when it comes to search, these are actually the GPS coordinates. Think of a possible traffic or delay, or even when you find the driver, like the match, it should be perfect. It should be the one that is close to you, because otherwise it will take a very long time and it won't work for the driver and also for you. So this is an important point here. Tinder is another great example of searching and of the search experience because you do that by yourself. When you say yes or no to people, what you're doing is you're filtering a data store, you're filtering a database. So this is another great example beyond the search box. Search is a constant, it's a foundation, it's everywhere. I like to say that, well, if you have data, you can search, and if you do it well, it will be even better. So think about your logs, metrics, traceability of your application. We are talking about AI here, but there is the observability aspect of it because there are logs for it, right? And it needs to work and work really well because you need to have all of your backend also working and everything that is the background too. So this is really important. Let's reveal here a typical search architecture with Elasticsearch before we proceed. So as expected, we would have the ingestion part here. We have 200 plus connectors, so you have a lot of options here, but agents, web crawler if you want to. So first part, to put data into Elastic, so to get data, collect data from somewhere. Then if you want, you can enrich data, so you can use Logstash, created by Elastic, ETL, any other that you want. You can also add it here, or use it directly anyways, if you prefer. It's completely RESTful. You can also consume it for there. And then your goal here is to store data into Elasticsearch. So basically, we call this, and revisiting for the others that are not used to Elastic, we call this indexing data into Elasticsearch. So you store your data into Elasticsearch this way, and your index will in fact be a collection of documents. And these documents are a collection of fields with many field types here. So here we'll cover some of these, actually 3 different field types. But this is where your data will live. And then finally, with the data into Elasticsearch, we're able to perform search. So this is the last step here. You can use Kibana too. You can create awesome dashboards. You can generate PDF reports, alerts, manage the health of all of your stack and everything. But as mentioned, it's completely RESTful. So you have your documents into Elasticsearch, and you can just consume it from there and customize your web app or your mobile app or what you're doing with it. Let's revisit text search then, the lexical search. So this is how it works. This is a sentence, and as an example here, of course, the best way to secure Elasticsearch. So what happens here is a process called tokenization, which is basically to divide your sentence into words. Here, I'm not doing anything fancy. I could add filters, for example, I'm not, synonyms too, I'm not. I'm just using a simple stop word removal, a simple analyzer and nothing else here. So as you can see, we have 1, 2, 3, 4, 4 tokens in this case, so 4 terms. And then with it, we perform the lexical matching. So we use the BM25 ranking function, which is a formula basically. And how it works, well, it will measure the relevance based on the frequency of these terms that you just saw and the rarity of the terms that you have considering all of your documents. This is the search architecture revisited for this case specifically. So basically, you have the app data, you store these into Elasticsearch. We are talking about text here, so it will be a text field in this case for full text search. And then the other side, you have the query, so the question that the user have in this case. And then with the text from the other side too, you perform the BM25 search in order to find the most relevant results here. Text search is useful for many use cases. I think we've been talking about text and full text search for a very long time. So this is really popular. We have this in different apps here. I think we are kind of like use it too. And that's because it's well understood. It's interpretable. As we saw, there are terms, there are filters, synonyms, you know the synonyms, so it's kind of like you can check it. The terms that you have, the terms that were generated, the formula itself, you can check it too. So it's pretty much simple to work with it, and we've been working with it for a very long time. But where it may fall short here, there is a point. One of them is the vocabulary mismatch. So in this case, for example, there are some research that says that same specialists from the same area, they can call this exactly the same thing, describe exactly the same thing using different words. I think I do this all the time. Like I use different words to describe things. We do this all the time. And this is a point here, as you saw, it's a literal match. It's an exact match. You will miss it. There is no way, unless you know all of the possibilities, all of the variations, all of the chains and the people that are going to query your data, it will be very difficult and you'll probably miss a good amount of information and you won't find the matches. So this is a problem. Another point here is the context, what we call the semantic mismatch. If I say here that Apple is going down, I think you probably know that I'm probably talking about the stocks, right? I'm not talking about the fruit. My mom would probably think that I'm talking about the fruit. So she would miss this. And this is a problem too, because she wouldn't find the match. So this is something for text search that we need to pay attention. Users expect more from search. We expect more from search. So we want to retrieve results based on intent, on context, on everything that comes with it, right? We want it to work. And then vector search enables semantic search. What is vector search then, this thing that people are talking about all the time? So basically, it's search based on vector representations, the embeddings. So this is a simple flow here. You have the documents, you generate the embeddings, in this case, a text embedding, but of course, it can be for other kind of data, image, for example. And then you perform vector search to find the top k number of nearest neighbors. So in this case, let me explain how it works. So the embeddings represent your data. Here we have an example of one-dimensional vector. So what we have here are two different aspects of the data, so ranging from realistic to cartoon. And we have something that I hope is a real elk, or it should be. And the other side, we have a cartoon version of this elk. I like to call this the student elk. So here we have different aspects. And then the dimensions, multiple dimensions here, will represent different aspects of the data. So I am also adding here mammal and bird, and the same thing with all. So in this embedding space, similar data are grouped together. So as you can see, the student elk, they have like, I have like more of this, so he has friends now. Same for the all birds too, and here it goes. In the end, when you perform vector search, it will rank objects by similarity to the query. So here we have the student elk again, and I am performing here the vector search, so this is the query. As you could see, the vectorized, which means the vector representation of the student elk is really close to the most relevant results that we have, which are actually the other cartoon versions of the elk. So in the embedding space, the query and the data itself that are relevant are really close to each other, and this is how it works. What I just said in another way here, this is the conceptual architecture. So you have the vector representations of your documents, and then the other side you have the query, and you vectorize this query, you generate the embedding for the query, and then once you have the two of them, you perform vector search. Well, I missed something here, right? How to generate context-aware text embedding, otherwise it wouldn't work like that. So this is a point here, and you apply natural language processing model, a transformer model. So basically with Elastic, you can import and deploy proprietary or third-party NLP models. So you basically, if you want to use Hugging Face, which is in this example, for example, Hugging Face, you select the model, you copy the name, you use our client, the Python client that we have, and then by selecting the task type, text embedding, you are able to import these into Elasticsearch. So you just deploy it and use it from there. If you have your own model, you can do this. So this is another possibility. And then with it, it just needs to be a PyTorch model, and you use the client directly and import these into Elasticsearch. When it comes to generating embeddings with Elastic, you have two options. So you can generate the embeddings inside Elasticsearch, which is basically what we just saw. You have the app data, you have it stored into Elastic, you need to generate the embeddings, so you do this before storing this through an inference pipeline. And then the same thing happens for the query, because you need to generate the embeddings too. So you do this into Elasticsearch. You perform inference into Elasticsearch. Or outside, which is basically you just come up with the vectors, which is also possible. I'm waiting for that picture here. Took the photo? OK. Then dense vector retrieval, what we just saw, performs really well. And this is cool because, as you could see, it takes into account semantic. Of course, if you have a great model, it will be even better. If it's not working, you switch models and use another one. So here it goes, but it takes semantic into account, which is really good and important. So it can beat other approaches for semantic search, for text search, as we saw earlier, because of semantics. But where it may fall short here, domain adaptation. So if you work for a very specific industry and you have a lot of keywords or terms or ways of saying things that are very specific, I'm pretty sure it will be hard to find a perfect model. Of course, you can fine-tune your model, you can retrain the model, and of course get better results, improve it. But in the end, it will be more steps. So you just need to make sure if this is what you want. There are other alternatives, like a RAG architecture can provide context, and here it goes. But again, more steps. So you just need to know if it makes sense. And the other point here is that it's not easily interpretable. So as we saw the exact match with the lexical matching, the terms, and then you can just check, well, there's something missing, so I will add a new synonym here, and I will try to fix this. Well, this is not the case here exactly. If there is something, if it's not working, you will probably check the model itself and see the accuracy of it, the data set that it got trained, and all of it. So this is a point here. It's not something that you just go there and fix it really quick. So this is not the point. Here is something that I like to talk about. Usually when I tell people about, let me even go back to the other slide here before the spoiler, but usually when I tell people about semantics, they want to do this, and then when I tell people about all of these points here, the domain adaptation, not easily interpretable, they ask me, well, is there another way of me, because I like of me doing this, because I like the things of having the term matching, I like the things of using inverted index, BM25 too, so is there a way to at least have like a bridge between the two, something that I can do with a sparse retrieval, another kind of possibility here with inverted index too. So in this case, it's not BM25, but there is something. It's learned sparse retrieval. So now, yes, it's an alternative approach for semantic search, and it will provide trade-off over dense retrieval and traditional sparse retrieval methods, as we saw earlier with BM25. So this is a good one to talk about. And what it does is something called term expansion. So basically, it will identify the contextual importance between the terms. It is pre-trained, so it will identify the relevance, the importance of the terms, and then it will utilize this knowledge to improve the sparse embeddings. Let's consider this example here. We have a query, comfortable furniture for a large balcony. Let's consider that this is an e-commerce website and the person is looking for it. This is one document, of course, you would have more, otherwise this is a match. But then the document says, is a comfortable and stylish garden lounge set, including a sofa, chairs, and a side table for outdoor relaxation. Well, this is definitely a comfortable furniture for a large balcony, so, I mean, it works. But at the same time, all of this description and everything from it all, the only match that we would have with lexical search is comfortable. So we will probably miss this, right? And then with term expansion, on the other hand, you have more matches. So for comfortable, you would have landscape, relax, calm, sleep. For furniture, sofa, couch, chairs, and here you go. So you have more terms here, which in the end, as you can see, we have more matches. So now, this document, I can see many terms here from what I had. Elastic provides a built-in option for this approach. So this is something Elastic provides, this pre-trained model, and to use that, you just download the model, and then you start the deployment, and it is like this, and that's all. Learned sparse retrieval is an improvement over text search, the lexical search we saw initially. Well, where it works here, it's well understood, it's interpretable, same kind of idea here, because you have the tokens, you can see a list of tokens, you can check it, so it's good for, even like if you're already using BM25, you like this kind of search, that's fine. If you're using to sparse retrieval, that's great too. But at the same, and also the vocabulary and the semantic matching, which is something that it provides, so it's an improvement here. But here, where it may fall short in this case is that, as expected, you would have a larger index because you have more tokens, you have more terms. Of course, I can say the same for dense retrieval too, if you have high dimensionality, but comparing specifically to lexical matching, then you can see that you have more terms in the end. Another point I can mention is that dense vector retrieval can outperform learned sparse retrieval for semantic search. if you fine tune the model, for example, or if there are many models out there, so there might be something that will work for your use case and it will be good, for example. So it really depends. So, but you can definitely find a good model when it comes to dense choose. So this is something to keep in mind. Well, is a combined approach a better idea? This is a good point here. Sometimes we just choose one, right? And we think that this is the answer. I'll just choose one of these options she mentioned, and then that's it. Well, it depends because there are use cases that will work better with one, and another use case that will work better with another kind of retrieval. So it's really, it is really something that you see in practice, that you test, and you will know what makes sense. But what is possible, and Elastic in this case offer two options here for you to do this, is to perform hybrid retrieval. Because then you can take advantage of both words, the lexical search word and the vector word with sparse and dense embeddings. So to do that, with Elastic, you have like these two options, a linear combination, which is basically a manual boost. You just say, well, this scoring method is specifically is relevant, like it's more relevant than the other. And here it goes. And you have reciprocal rank fusion, or F. There are lots of papers comparing both, and then you can see what makes sense for a use case. Most of the time is or F, so you can just try it out and see what works. But in this case, it just, instead of you manually boosting it and say, manually boosted is basically like multiplying by. So instead of doing this, you just have a blend of the ranking methods. Everything you've heard here is powered by Elasticsearch, Relevance, and Gene. So we offer a vector database or F, so we can perform hybrid search here. The ability to host your transformer model, as we saw earlier. Elastic proprietary ML model, as we talked to. Integration with other third-party NLP models, transformer models, specifically OpenAI, for example. And integration with other third-party tooling like LangChain. My invite here for all of you is to join the Elastic community. So first link here, the Search Labs. This is really good, and we are updating with lots of demonstration, open repository, open code too. So you can just navigate and see if there is an example. So we have many. You can try it free on Elastic Cloud. So there is a free trial available. Just go there and check it out. And of course, if you have questions, we have a great community. So it's really nice to answer your questions as mentioned. So just let us know. Thank you. And before I finish this, we will have the session upstairs. So if you have any questions, you can also go there. I think we have time probably for one question here, so just let me know. We have the booth there, so if you've not been there, we have some demonstrations comparing these retrieval methods. So it's nice, you can see the difference using one or the other. And again, this is my contact info, and the QR code is for my LinkedIn profile too, so just feel free to connect there. That's it. I have, okay, so any questions? You have one? Is there a microphone?
No, he will ask the question and you repeat the question here.
Talk a little bit more about the performance impact with the hybrid scoring, because now you have to maintain like a text, PM25 text, and the vector text as well.
I don't know if I...
Could you repeat the question louder?
Can you talk a little bit more about the performance of the retrieval part for the hybrid scoring? How you maintain like a text index, the text index, and the vector index.
Okay, performance you mean because you would need to store both, right? Yes. So Okay, so he's asking about the performance because, for example, for hybrid, if you want to do both, like BM25 and the dense vector search, for example, you would have to store both. So you have like the two fields, two different fields for the same kind of data, for example, and it will be more than you would have if you just have one. So this is the point of course, like the trade-off, I would say, when you are I would say like selecting your method, for example. But in the end, most of the times it's in fact good to have the lexical matching even as a filter. Because in the end, if you perform a lexical matching and you filter your data and you really have like less vectors to search within, then in the end, you improve the performance. So it's something that, of course, you need to take into account because you have both, but at the same time, most of the people already are storing the text as is, so it can make sense like for the use case to do both and then to use BM25 as also, besides of course being relevant for the end result, but as also a way of making sure there is enough filters and enough layers for the vector. You can. To have less dimensionalities, you mean? Okay, to just start with small pieces instead of like the entire document if it affects the performance. All right, so definitely you can like just add small pieces, but the point is if it describes everything that you want to, so it can affect the performance or not. It depends on your approach, on what is your goal, and if it's covering everything. But it's definitely a use case that's out there, and there's definitely people doing this too. So there's no like, I don't have like one answer for this. It depends, but of course, if it's doing what it needs to, then that's okay.
One last quick one.
Okay, how do you define like if you have something domain specific, like the term expansion dictionary, or how to manage that?
For term expansion, you mean the domain specificity for?
I guess like adding additional terms to that term expansion.
Yeah. So in this case, this is a pre-trained model, so it's as is, basically. So it's called ELSER, so you can look for it and you can try it out. We are improving it very often, so we'll launch other versions too. So this is something that we want to keep investing in and something that we are also looking for feedback. But this would be like, that's why I mentioned this as a trade-off, because in this case, you would have it as a built-in model.
Thank you.
Okay, cool. So I'll be there upstairs. If you have more questions, just let me know. Otherwise, thank you so much for your time today.